of springs here. We have a mass spring system oscillating back and forth. We're going to assume a frictionless situation. Of course, if it was friction, it would slow down after time. Okay. And we are going to look at the period of this. The period of this oscillation is going to equal 2 pi. Okay, then that would be times the square root of m over k. And k is the k constant for the spring. Okay, now remember though, if I want to get the frequency, frequency does equal 1 over the time, 1 over the period. The frequency is the number of oscillations that will happen through time. Okay, so let's say I pull this a distance. This time it'll be to the right. Okay, so what would our graph look like as it oscillates back and forth through time? Each one of these lines represents 1/4, okay, of the oscillation. Okay, I'll do that in green. So I'm going to put a dot here, one here, one at this position, one here, and then one back up there. And then this is what our cosine graph is going to look like here. Okay, now remember omega, okay, is angular frequency, does equal the square root of k over m. And our graph, x, is going to equal the amplitude, how long I stretch it, okay, multiplied then by the cosine of omega t. Okay, so it's going to oscillate back and forth, and we know the displacement. Okay, now velocity, you're going to be not moving at all here. When it gets back to equilibrium, that'll be maximum velocity, and then it's going to crunch together and come to a stop, and then it's going to go back and forth like that. So velocity is going to be a sine wave, okay, and what we're going to do then is we're going to have a negative sine wave. So I'm going to start here at 0. We're going to go to a negative, okay, value here, and then we're going to go back to 0, and then to a positive value, okay, and then back to 0. So we put lines for those. And then let's draw what that looks like. So this is a negative sine graph. It's negative because it's the opposite. Okay, the velocity will be negative when it reaches equilibrium, then go all the way to 0 again, then back to a positive at equilibrium again. And equilibrium for this would be no stretch at all. So back and forth. So this is going to be the velocity. It's going to equal negative a times omega, and then times the sine of omega t. Okay, now continuing to the acceleration. Okay, at this point we're going to have maximum acceleration, and that'll be towards the negative direction. Okay, and then we're going to come to 0 when we're at maximum velocity, right in the middle where the spring is not stretched. And then we're going to go to positive acceleration as the force is the greatest, and then back again to 0. Okay, and that's how it goes. So let's start off with, let me use red here. So when we're here, we have the greatest force. So that's when acceleration is going to be a negative because it's going left. Okay, and then we are going to then go to 0 acceleration when the spring is not stretched, there's no force acting on it. Then it's going to get all crunched together, and I'm going to make a positive maximum acceleration, wanting to push it back in this direction because it got all scrunched together. And then back to 0 again when we're back to the spring not being stretched. Okay, and then finally back to a negative when we reach this position where the string is stretched the most and it wants to pull in that direction. So this is what our graph is going to look like here. Okay, and then acceleration then is going to equal a negative a times omega squared times the cosine of omega t. Okay, so that's what our graphs look like. Now, potential energy versus time is going to just be really U is going to equal simply the change in kinetic energy. That's what's going to be going on here. Okay, so basically what's happening is potential energy maximum is going to be here, then we go to kinetic energy, then potential, then the kinetic, then potential. It goes back and forth like this. So I'm going to start with a maximum potential energy here. I'm going to go to 0, back to maximum again, back to 0, back to maximum again here. And this is what our graph is going to look like for potential energy of a spring, okay, versus time. Then again, you can just do change in kinetic energy, or you can go 1/2 kx squared, whatever it is you want to do. Now for a vertical spring, the only difference is we will have an initial stretch, okay, and you can call that 0 for now, but to get that stretch, you have to remember that downward is force gravity, and upwards is the force of the spring. So to get the initial stretch, okay, you can just do kx, okay, equals mg, and k, of course, is your spring constant. So just divide k into that, and you'll get your x. Now again, all the graphs are identical, so you can treat this as if it was oscillating back and forth horizontally. The graphs are identical. Just have to remember that there is an initial stretch here. Okay, next. What if I have two springs? Now this is for my mechanics C people. Okay, if I have k constant on both sides, the period of this, the only difference now is it's 2 pi square root of m over 2k, because there's two springs of the same value there, and of course omega will equal then the square root of 2k, okay, over m. Okay, now the rest of the stuff I'm going to talk about after this is going to be from our mechanics only, but let's do pendulums really fast. So of course we measure the pendulum angle here. We do measure height by equaling L minus L cosine theta. Okay, so when we do the period for this, it's equal to 2 pi square root of L over G. And remember, L is the length from the center of this all the way to here. That's the length L. Just do little dashed arrows like this. Okay, and we have to remember that omega this time does equal the square root, okay, of m g L over moment inertia I. Now this part's more for my mechanics C students here, because we have to remember that the restoring force, okay, in this situation, we'd have gravity straight downwards like this, force gravity, like that. And here's our little triangle that we draw. This, of course, is our theta. So we have to remember that torque, of course, does equal I alpha. But in this case, it also equals mg L sine theta. Now remember, theta at small angles is approximately equal to the sine of angle theta. So really what we have is I alpha is equal to mg L theta. Okay, and this essentially is our k effective here. I can write this as a second order differential equation. We have I equals the second order derivative of theta with respect to time equals mgl theta. Okay, and if we got that, we know that we do a simple harmonic motion because we have a second order derivative equal to a linear k constant. Now remember, this only works when we're very close to 0. It seems like it works actually good from 0 to 20 degrees. Okay, now of course, going back to our mass spring situation here, we of course have a force that's a restoring, so we have kx, okay, which is our spring constant, okay, multiplied by x, okay, and that of course equals the force of the spring. Now I can, if we look at this, we remember that the force of the spring does equal the acceleration. So I'm going to rewrite this. So we have m times a equals kx. Okay, k of course is what's called k effective. It's our spring constant. So I can write this as m times the second order derivative of displacement, okay, with respect to time, equals kx. So we have a linear restoring, okay, x to the first power here, and we have a second order derivative, okay, and an m, of course, is a constant. Okay, so we know that we have simple harmonic motion here. Save.